Hello everyone, I'm Ze Yujing from Scripps Institution of Oceanography. It's my pleasure to share with you results of our work that were recently published in JGR. In this paper, we used 5 years of InSAR and GNSS observations to study the Lithospheric deformation due to 2015 magnitude 7.2 Pamir earthquake that occurred at the northwest margin of the Tibetan plateau. Large earthquakes are typically followed by slow deformation that results from redistribution and relaxation of coseismic stress changes in the host rocks. The pattern and rates of postseismic deformation can be used to learn about the properties of rocks at depths, which provides us with a possibility to infer the rheology of the lithosphere beneath the Tibetan plateau. There are several schools of thought on the mechanisms behind the long-term uplift and the evolution of the Tibetan plateau. One model suggests that the collision zone consists of blocks that are bounded by deeply rooted faults, and the crustal deformation is mostly accommodated by slip on these major faults. In contrast, it was also suggested that a weak layer in a lower crust may decouple the underlying deformation from the upper crust. The key difference between these two conceptual models lies in the effective viscosity of the lower crust and the upper mantle beneath the Tibetan plateau. Viscoelastic relaxation of the stress changes caused by the large earthquakes would generate observable postseismic deformation signals, which could be used to distinguish between various conceptual models. In this map, black beach balls denote previous earthquakes that occurred on the boundaries of the Tibetan plateau in the last 20 years, and the red beach ball denotes the 2015 magnitude 7.2 Pamir earthquake that we used in our study. Here we show a comparison between the observed line-of-sight displacement spanning about 5 years following the main shock from the ascending track of Sentinel-1 satellite, and predictions of a viscoelastic model that assumes a relatively weaker lower crust. Positive line-of-sight displacements correspond to surface motion towards the satellite. The data reveal a sharp step in the line-of-sight displacements across one of the branches of the earthquake rupture, which we attributed to shallow afterslip. Although the data coverage away from fault is limited due to decorrelation, we do not observe the quadrants of uplift and subsidence expected in the bulk viscoelastic relaxation below the brittle ductile transition. We also processed far-field GNSS time series to place further constraints on viscosity of the lower crust and upper mantle beneath Pamir. Here we show a comparison between the observed GNSS time series and predictions of several viscoelastic models, assuming viscosity of the lower crust ranging from 10 to 18 to 10 to 20 pascaseconds at the respective GNSS site locations. Color shading represents an admissible range of model predictions due to uncertainties. Our model sensitivity tests reveal that the time series are consistent with the viscoelastic model, assuming viscosities of both the lower crust and upper mantle greater than 10 to 19 pascaseconds, which is denoted by magenta lines here, suggesting a rather small contribution from viscoelastic relaxation over the period of observations, which agrees well with our InSAR results. In summary, we find that the near-field postseismic deformation after the Pamir earthquake is dominated by shallow afterslip, with a possible contribution of poroelastic relaxation at the northeast end of the earthquake rupture. Our data do not show a clear signal expected of viscoelastic relaxation, indicating viscosity of the lower crust larger than 10 to 19 pascaseconds at the northwest margin of Tibet. For more details, please visit this link and read our paper. Thank you for listening.